Thank you for that kind introduction, Jennifer. As she mentioned, my name is Aparna Skralik. I'm with the Aurora Group. We're a manufacturer's representation firm. And today we will be talking about the guidelines for surface mount electronic fuse selection. Before we get started, just a few words about the Aurora Group. We're a manufacturer's representation firm serving the Southeast and the East Coast with over 30 years experience. We cover the full East Coast. Our particular group covers North Carolina, South Carolina, Georgia, Alabama, Mississippi, and Tennessee. What we do is we are committed to facilitating electronic and mechanical component solutions for OEMs, CMs, and engineers. And we accomplish this by providing technical information and training such as this, advice, support of quality manufacturers that we represent, guiding through the technical challenges with new and existing products, and offering component liaison quotes, ordering, expediting, and other support. We are your one-stop call for these manufacturers. Here's a quick look at our group. You may know some of these faces, may have seen them over the years. We serve all markets. Anybody that uses electronic or mechanical components, feel free to reach out to us and we could probably help you with at least a few of these solutions. Our current line card looks like this, and we are very proud to present today a bit more about electronic fuses. Our technical talk will be done by the technical manager of AEM Components. A bit about the AEM Components. AEM Components is a true manufacturer of intrinsically safe SMD fuses, and it is the second largest manufacturer of SMD fuses worldwide. Today, we're honored to have the technical manager from AEM Components to present the detailed calculations for SMD fuse selection and derating calculations. AEM Component manufactures resettable fuses and patented construction fuse models that you may have heard of, such as the solid matrix, air matrix, and the CMF high power fuses. In this presentation, you will learn the calculations and formulas for derating under conditions of steady state, transient conditions, multi-pulse, single pulse, and temperature. These factors should always be considered when selecting SMD fuses. And now I'll turn the screen over to Mike Roach.
Thank you very much, Aparna. Before we get started here, I'm going to have to switch over and take control of this screen. But before we get started here, I'll just tell you a little bit about myself. As Aparna had mentioned, I work for AEM Components. I'm the technical sales manager for this company, having worked with them for about 7 years. But I've been in the passive industry here for a little bit over 30 years right now, focusing primarily on capacitors. And then about 7 years ago, I came over to work at AEM, working more so on fuses. A lot of commonality between fuses and the passive components that I worked on. But the one thing I found out very quickly about fuses is that they're not as simple as one might expect or one might think. They often involve a lot of different considerations, as Aparna had mentioned, related to temperature, related to current rating, related to a number of different things that may come into play depending on a customer's circuit. I am basically going to turn my camera off here so I can focus on the presentation itself, and then just keep talking about fuses. Basically, this presentation is going to discuss fuse selection guides and methodology for one-time surface mount fuses. And what I'm going to cover in this presentation is a number of different factors. I'm going to cover basic fuse functionality, what you might expect for a fuse when it's in the circuit, selection parameters overview, basically what you need to consider when you're choosing a fuse, and they would involve such things as steady state considerations, transient state considerations, and safety considerations and regulations. I'm going to summarize this by going through the selection methodology step by step, and then I'm going to provide you an example at the end of all of this so that we work through an actual real-world fuse selection process. So basic fuse functionality. really a fuse should be invisible to the circuit under normal operating conditions. A fuse is basically a piece of wire. So it would be similar to what you might see as a trace on a circuit board. So if the circuit is operating as intended, you shouldn't even know that fuse is there. But if you do get an overcurrent event of some sort, the fuse is intended to protect downstream components during an unintended overcurrent event. How does a fuse basically work? Generally speaking, the fusing element is made from metal, and that metal will melt if it's subjected to a sufficient overcurrent. In other words, if the current goes up, the metal gets hot. If it gets hot enough, then the metal melts and the fuse opens. Fusing characteristics and effectiveness of the fuse can be affected by multiple factors, including the ambient operating temperature. What's the maximum temperature that the part might be exposed to in the application? If it's subjected to pulses, current pulses of some sort, the shape, amplitude, and duration of those pulses, and the number of pulses can also affect the performance of the fuse. And though you really don't consider it while the fuse is operating as it's intended, or in a circuit without any sort of pulses, operating voltage also plays a significant role in the event that the fuse were to open. Another thing that you need to consider is that similarly rated fuses can have different fusing characteristics. You have the application of slow blow versus fast acting fuses. If you guys have heard that terminology before or not, a slow blow fuse is generally intended for those applications that would have a motor. Let's say for a power tool, for example, there's generally a high inrush current when you power up a drill, for example, or if you're drilling something and you get a motor lock because the drill bits get stuck, you get a high inrush of current. So you'd select a slow blow fuse for that because those type of fuses are intended to accommodate those current inrushes without actually opening. A fast acting fuse on the other as another example is intended for sensitive circuitry. You might want to consider using a fast acting fuse in home appliances or computers where any sort of a inrush current for any extended period of time might cause damage to sensitive and more expensive components downstream. So you'd select a fast acting fuse in that case. And then the other thing that you need to look at when you're talking about fuses or you're comparing fuses is that there's manufacturing differences. One manufacturer or supplier could build fuses slightly different than another manufacturer, and those differences can affect the performance of the fuse.
Mike, I have a question for you.
Sure.
Your slides are showing in non-presentation mode. Is that how you wanted it?
Shouldn't be. Let's do that again.
There we go. Excellent.
Okay. So your application defines required upper and lower fuse current ratings. So if a customer were to provide you with a specific application, that application would define both an upper and lower fuse current rating, and those current ratings are governed by three basic parameters, including steady state conditions, transient conditions, safety standards and regulations. The upper limit is generally intended to protect downstream components and takes into consideration safety regulations like IEC or UL. The lower limit, which deals with steady state conditions and transient conditions, basically helps you to identify the minimum current rating that you would need to select in order to operate in the application. Steady state conditions are basically broken down into two steps. There's a basic safety standard derating factor, which I'll talk a little bit about more in a second, and then a temperature derating factor. From a transient state condition, this is where you start talking about interrupting ratings and nominal melting integral, or more commonly referred to as the I²T of the fuse. And then in safety considerations, you're looking at clear time characteristics, the voltage rating of the device, and safety standard requirements, which would be UL and IEC as an example. So for steady state conditions, the maximum steady state operating current is the first thing that you're looking at. And the minimum fuse current rating versus the maximum steady state operating current is defined in accordance with international standards, where the fuse must function at 25 degrees C for 4 hours at the circuit current, steady state circuit current for 4 hours minimum. In order to do that, UL and the safety standards have implemented a derating of 75%. In other words, you take the minimum fuse current rating, and you establish that value by taking the maximum steady state current rating of the circuit, and you divide that by 75%. So if, for example, you're looking at a fuse current, or excuse me, a circuit current of 0.6 amps maximum, you would divide that by 75%, or 0.75, and the fuse you would select at that point would be 0.8, so slightly above the actual current for the circuit itself. The next thing you look at is operating temperature. As I mentioned before, these fuses generally have a metal fuse fuse element that they use, and copper is one of the more common ones that they have out there. So copper exhibits a positive temperature coefficient of resistance of plus or minus 0.393% per degree C, reference to 25 degrees C. So if you think about that, the fuse ratings that you look at in the catalog are generally rated at 25 degrees C. But if your actual application temperature would be above or below that, then that would affect the resistance of the fuse. Now, it's not a problem generally when you go below 25 degrees C, but when you go above 25 degrees C, you generally have to derate the fuse because the resistance is higher. So the fuse doesn't function the same way it would if it was being operated at 25 degrees C. So there are curves put together that manufacturers will provide. You see some examples of some curves on the lower right-hand corner. So let's say that for this specific application that we're talking about here, that 0.8 amp fuse that we had selected a little earlier at 25 degrees C is actually operating at 65 degrees C. Then you would derate that. In this case, the derating would be 0.9. So that 0.8 amp fuse now becomes 0.89 amps. All right. So you can see again, temperature will require, if you're operating above 25 degrees C, will require that you derate the fuse there as well. Transient conditions. Interrupting rating. Interrupting rating is defined as the maximum current that can safely be interrupted by a fuse while operating at rated voltage. These ratings are established through internal testing at various overload current conditions. In other words, they'll take a fuse that's rated for, 0.8 amps, and they'll subject it to increasingly higher levels of current. And they get it to the point where they'll take that fuse to the point where a certain current level will cause damage to the fuse itself, which is something you really don't want to happen, because in those sort of situations, you could cause collateral damage to components around it, or the fuse may not open as intended. So when you establish, or when you select a fuse based on interrupting rating, you want the interrupter rating of the selected fuse to be greater than or equal to the maximum fault current of the circuit. So proper selection ensures the fuse will break safely without creating collateral damage or hazardous conditions. If you take a look at some examples at the bottom, you can see the fuse on the left there. The solid matrix fuse provided by AEN Components has a robust solid body construction with fuse elements centered in the ceramic body. And this type of construction helps to contain the energy during an overcurrent event. Still looking at the pictures to the left, if you look at the middle picture, you can see what happens to the fuse elements if it sees an overcurrent event. Those fusing elements or metal are actually diffused into the ceramic. And the picture to the right of that middle picture there shows you the fuses after the fuse is open. There's really no change in appearance to those fuses, and they've maintained their mechanical integrity. There's been no smoking, no cracking, and no collateral damage to anything around those fuses. Looking at the more conventional chip fuses to the right, this type of construction has a fuse element placed on top of a substrate, and that fuse element is coated with a polymer. And if these type of fuses are subjected to a higher overcurrent event, that polymer has a difficult time containing the energy. And in some cases, that epoxy or polymer will melt. You can get smoke and you can get some fire in those type of cases. Generally, these type of fuses tend to be lower voltage fuses, lower current fuses in a lot of cases. So the damage may not be as severe, but there still is the risk that you will have smoke and you will have potentially fire in some extreme conditions, which is not allowed by a lot of the safety standards that are out there. Interrupting rating is the second step that you need to look at here for transient conditions. And um, I'm sorry, let's go back to the interrupting rating again. These are some other examples of the interrupting rating right here. So in this case, the other ones before were solid body fuses with the fuse elements either on top of the directly on top of the body or the housing or inside of the housing. And in this case, these are wire and air fuses. And wire and air fuse, that terminology is pretty common within the industry. And you can see a couple of different examples here as well of wire and air fuses, where AEM's air matrix fuse on the right is again a very robust solderless construction. I think the solderless point of that is pretty important. The fuse elements are centered in the flexible FR4 body, and this construction, especially with no solder in there, helps to contain the energy during an overcurrent event. If you look at the picture on the right, for example, those type of fuses have a ceramic outer housing and they have a metal fusing element inside of that body, and it's soldered in either end with a blind solder joint, and they need to use generally a significant amount of solder inside of those parts in order to ensure they have the connection. So you have inconsistent fuse element placement and the use of solder internal to the cavity. So this type of fuse has a difficult time containing the energy during an overcurrent event, especially a worst case condition. Looking at the pictures on the bottom, all the fuses that were tested here were 1.25 amp fuses, rated for anywhere between 125 volts DC to 250 volts DC. The currents that they were subjected to again was 400 amps, 250 amps, and 400 amps on the right at different pulse voltages. You can see the ones on the left after the test, the air matrix parts, they've again maintained their mechanical integrity. And if you look at the wave shape that you have there from that screenshot, you can see that the current, which is the gold colored wave shape, goes up. It exceeds the breaking point of the fuse element at 400 amps, 250 volts, and that wave shape basically goes back down to zero. It's a very smooth shape, and the voltage rating across that, which would be at zero, as I mentioned, before the fuse opens, the fuse acts, it's invisible to the circuit, so there would be no voltage across it, a very amount of voltage drop across it. But after the fuse opens, and you've got an air gap in there, so you can see that when the current goes down, the voltage goes up to its maximum. Looking at the examples on the right, again, I mentioned these type of fuses, not only do they have the metal fusing element in the middle, they also have a lot of solder in there. And as I mentioned earlier, when a fuse opens, it opens because the fuse element has melted. So you're talking about a really high temperature. And at those current ratings that you're talking about below, not only does it melt the fusing element, it melts the solder inside of that cavity as well, causing the solder to vaporize and pressure to build up to the point that the fuse basically erupts in a destructive manner. There's a redeposition of all that metal across the boards, and you get considerable collateral damage and post-arcing, which is the burning that you see in that picture to the left on the bottom. So getting into the next section here, this is the nominal melting integral, or the I squared T, which is the second part of the transient conditions that you need to consider. Now, nominal melting integral of a fuse defines the amount of energy required to melt the fuse element and cause the fuse to open. Components within the circuit can generate energy in the form of a transient pulse during switching cycles. And proper selection ensures that the fuse can operate as intended without opening prematurely. The fuse rating, I squared T, must be greater than or equal to the I squared T produced by the circuit, a calculation that we're going to go through right now. So when you're talking about I squared T, you're talking about a number of different wave shapes. So these are basically pulses, different pulse types that depending on the circuit, the fuse might be subjected to. You've got wave shapes like square waves, sawtooth, sine waves, decaying waves, those sort of things. And each one of those would introduce a different I squared T to the circuit, with the square wave being the highest, presenting the highest I squared T to the circuit. So down below, I've shown some calculations where I've calculated the I squared T for a square wave and for a sine wave. So a square wave transient pulse would require a fuse rated for twice the I squared T of a sine wave, just basically looking at that calculation. And the I squared T is calculated by taking the peak transient waveform pulse, squaring that value, and then multiplying that by the pulse width in seconds. So if we're considering a pulse that has an amplitude of 45.5 amps for 1 millisecond, the I squared T produced by that wave shape would be 2.07 amps squared per second. A sine wave, as I mentioned, produces about half the I squared T of a square wave. So the I squared T for the sine wave would be 1.035 amps per second. Should be noted looking at this slide that this calculation is based on a single pulse. But most circuits produce more than a single pulse. You can have multiple pulses that the fuse is going to be subjected to, and you need to take that into consideration as well. So if you're looking at the pulse derating of a fuse, there are some standard derating factors, P, that you would apply to the previously calculated I squared T. If you expect the fuse to be subjected to 100,000 pulses, for example, you're going to derate that I squared T calculation that you previously did to using a 20% derating factor. 10,000 pulses would be a 30% derating factor, and even 1,000 pulses would require that you derate the fuse using a 40% derating factor. So looking at those I squared T calculations that we had from the previous page, the square wave, which we originally calculated at 2.07 amps squared per second, would now require, this fuse would now be required to meet a minimum of 10.35 amps squared per second. Similarly, for the sine wave, where we had calculated an I squared of T of 1.035 amps squared per second for a single pulse, at 100,000 pulses, you would now require a fuse that has an I squared T minimum of 5.175 amps squared per second. As I mentioned earlier on when we were talking about the steady state calculations, we know that temperature can have an impact on the rating of the fuse. So you would also need to apply that temperature derating factor K to the I squared T calculations. So you've got, from the original, excluding the fact that the part may see multiple pulses, if you're just looking at a single pulse, and you were to apply that I squared T temperature derating factor, that 2.07 amps squared per second that we calculated for a single pulse, would now be 2.3 amps squared per second. And the temperature derating factor applied to a sine wave, where the original I squared T was 1.035 amps squared per second, would now be 1.15 amps squared per second. So you'd need to select a fuse that has an I squared T rating of greater than 2.3 amps squared per second if it's a square wave, or 1.15 amps squared per second if it's a sine wave. The last part of it here is the safety considerations. So in this section, we're going to look at clear times. We're going to look at the importance of voltage rating, and then we'll talk a little bit about safety standards and regulations. Clear time characteristics, also referred to as pre-arcing characteristics, establishes the estimated rate at which a fuse will respond to varying current levels while operating at 25 degrees C. So basically what you're doing is you're applying different levels of current, and you're measuring the time it takes for the fuse to open. This is typically listed in tabular form as a percentage of the nominal fuse rating, but you can also get it in graphical form for comparison between similarly rated competitive options. As I mentioned before, there are differences in the way companies manufacture these fuses. So if you want to take a look specifically at how one type of fuse would stack up against another manufacturer's fuse, you could essentially go to those pre-arcing curves. And there's an example of one there to the right. This also aids in the selection process because it helps to distinguish between fast acting and slow blow fuses or time lag fuses. Again, remember what how I define fast acting versus slow blow. Fast acting is intended for sensitive circuitry that cannot handle an extended pulse, and a slow blow fuse would be used in an application which is basically a motor driven application like a drill. Voltage rating. Voltage rating really doesn't become important until the fuse opens, but the voltage rating of the fuse must be greater than the voltage rating of the circuit itself. If you consider that a fuse voltage potential in air is dictated by the size of the fuse and the clearance between the opposing polarities, if your voltage is such that that clearance will not support that the differences in potential, then you're going to get arcing across that fuse even after it opens, which is something you don't want to happen. You basically want the fuse, if it's acting properly, to completely stop the current flow. So proper selection minimizes the potential for post-open arcing conditions. You just need to make sure that the size and the rating are correct for the specific circuit voltage rating. Certain wire and air designs, utilize materials intended to quench the post-open current flow, and they can improve performance. In other words, they'll fill that air cavity that's in there with a material that helps to quench the current, basically helps to shut it off, aids in the quenching function of the fuse, and that can help improve the performance. It also allows some of these fuses to be smaller in size if you're using some sort of filler material to aid in the opening or the quenching of the fuse after the fuse is opened. Safety regulations and standards. I'm really not going to get too much into this. There's final considerations that are based on established standards like UL and IEC, and those standards ensure fuse compliance and safety to someone that might be actually using a piece of equipment that has a fuse in it. So it's intended in a lot of cases to protect the person that might be using a particular piece of equipment. You could spend probably an hour or so just reviewing and covering different safety standards and what they mean in certain applications. So, I'd save that for another presentation than some other time. So the selection process in summary, it's really a 7-step process. And the first 2 steps, you're dealing with the steady state conditions, where first you apply the UL safety margin of 75% to the circuit steady state current rating, and that ensures the fuse is capable of handling the rated current for 4 hours minimum at 25 degrees C. So that's the first safety factor you apply. The second safety factor you apply, or factor you apply, I'm sorry, is the temperature derating, at which basically on those curves, as I mentioned, the fuses will behave differently and not have the same performance characteristics above or below 25 degrees C. And there's a derating factor that you need to apply dependent on the maximum operating maximum operating temperature that the fuse will see. The next step is the transient state parameter calculations. So you calculate the application circuit nominal melting integral for a single current pulse using the formulas for common pulse waveforms. If the waveform or the pulse that your circuit is producing is different than one of those waveforms, the standard waveforms, there are calculations that you can use to determine the formula for a specific waveform. So once you've done that, once you've calculated the I squared T for the circuit for a single pulse, you apply the pulse derating factor, which is step 4 in this. And that's based on the estimated number of pulses the fuse will see during the operational lifetime. After that, you apply the same temperature derating factor K, which was found in step 2 of the I squared T calculation. And based on the circuit I squared T calculation, you select a fuse with an I squared T rating that is greater than or equal to the I squared T value. And then finally, step 7, you'll take a look at the safety standards and circuit protection. You want to ensure the fuse complies with the applicable safety standards that may be called out, that the voltage rating is sufficient to prevent post-open arcing, that the clear time characteristics are sufficient to prevent the circuitry from overheating, and that the interrupter rating is high enough to ensure the fuse opens safely as well. So the higher of the two current values found in steps 1 and 2 versus steps 3 and 6 determines the lower limit for the fuse rating. So we'll see that when we get into the next calculation. Step 7 helps to determine the upper limit for the fuse rating, considering performance variations within the circuits due to other components. A lot of manufacturers will generally want to add a safety margin in there as much as 30%, and that's intended to prevent nuisance openings, right? Things that things that would cause the fuse to open that's really not something that you were expecting. So basically, when you choose a fuse, it's better to go with a higher rating as opposed to a lower rating if you've got more than one fuse to consider. Okay, here's the example that we're going to use, and here's the parameters. So let's say that a customer has an application where the maximum steady state current is a little more than a half an amp. The operating temperature is plus 65 degrees C. There's a sine wave pulse that is going to see with a maximum pulse current of 45.5 amps, and the pulse width is 1 millisecond. And the required number of pulses over the life of the device would be roughly 100,000. And the overload current and corresponding breaking time is 16 amps at 60 seconds. Possible maximum fault current in application would be 50 amps. So that's the worst case condition in a fault situation. The maximum operating voltage is 12 volts DC, and the fuse dimensions are 1206. 1206, if people aren't familiar with that type of terminology for dimensions, it's an EIA code where the 12 would be 0.120 inches and the 06 would be 0.06 inches in length and width. And then the compliance standard that these parts need to meet is a UL recognized standard. So the first step in the calculation is the steady state parameters. In this case, in this example, we've combined not only the current derating factor, but the temperature derating factor as well, because both would apply to this specific application. So in order to determine the minimum fuse rating that you would need here, based on steady state parameters, you would take the 0.54 amps and you would divide that by the 75% current derating factor and 90% for the temperature derating factor, which converted to decimal representation would be 0.54 amps divided by 0.75 and 0.90, which gives you a current rating, a minimum current rating of 0.800 amps. Rounded up to 1 amp. They're really, most manufacturers wouldn't manufacture a 0.8 amp fuse. And as I said, you generally want to round up. The closest common value for a fuse would be 1 amp minimum. So that's what you would select based on steady state parameters. So the current rating for the fuse based on steady state calculations would be greater than or equal to 1 amp. And that would be an acceptable starting point based on the nearest standard fuse rating. Getting into the calculation of transient parameters, you want to calculate the I squared T value. So this is a single pulse at 25 degrees C. And as I mentioned, we're going to use a sine wave here. So in order to calculate that for a sine wave, it would be 0.5 times the current rating, the steady state current rating for the circuit squared times the time of the pulse. Excuse me, that's not the steady state. That would be the peak current for the pulse squared times the duration of the pulse. So in this calculation, you have 0.54 amps times 45.5 amps times 45.5 amps times 0.001 seconds. And that gives you an I squared T based on a single pulse of 1.18 amps squared per second. So, so a fuse with an I squared T rating of 1.118 minimum amps squared per second would be required to handle a single wave pulse of 45.5 amps for 1 millisecond operated at 25 degrees C. The next one, the next calculation that we're looking at here is determining the I squared T impact of the pulse D rating and the temperature D rating. So again, we're combining both of these into a single calculation because both would apply here. So you would take the calculation that you came up with above for the single pulse of 1.118 amps squared per second, divide that by the pulse D rating factor for 100,000 pulses, and divide that by the temperature rating factor, K, at 65 degrees C. And in that case, working through that calculation, you can see where the I squared T of this particular fuse is increased from 1.118 amps squared per second to 6.21 amps squared per second. So a fuse with an I squared T rating of 6.21 amps squared per second minimum is required to meet a 45.5 amp 1 millisecond sine wave operated at an ambient temperature plus 65 degrees C maximum for 100,000 pulses. If you take a look at catalogs, and in this case, I'm looking at the AM catalog, and you look at the I squared T versus time curves, you can see that the fuse series F1206HI, so this is a high inrush current fuse rated for 6 amps, would have an I squared T of 6.5 amps squared per second at 1 millisecond, which would meet the I squared T minimum requirement of 6.21 amps squared per second that we calculated above. Now you can also note here that where we had with the steady state calculations, we had said we need a fuse that's rated for 1 amp minimum. Based on the transient parameters, you can see where that 1 amp fuse is now gone up to a minimum of a 6 amp fuse in order to operate in these in this environment or in this application. The next thing you want to do here is you want to determine the clear time characteristics of a fuse maximum current rating based on an overload of 16 amps and a required breaking time of 60 seconds. If 16 amps is 200% of the current rating of the fuse, then the upper limit would be approximately 8 amps. And now we're talking about an upper limit here of 8 amps. So comparing the required breaking time of 60 seconds maximum to the clear time characteristics tables in AEM's catalog, the solid matrix, again, the F1206HI series, would meet this requirement. In addition, the clear time characteristics for the F1206HI series establishes 16 amps is 200% of the fuse current rating at 60 seconds maximum, which would set the upper limit of 8 amps for this particular type fuse. All right, so that's the summary there. You want to confirm the interrupter rating for the fuse will meet or exceed maximum specified 50 amp fault current for the application. Again, going back to the AM catalog for the F1206HI, the 6, 7, and 8 amp fuses, remember we said you would want a fuse that's a minimum of 6 amps, and above we're saying the fuse should be in the range of 6 to 8 amps. Those fuse designs have an interrupting rating of 80 amps at the working voltage DC, which complies with the spec requirement of 50 amps minimum for the fault current. And then the final thing that you would do here is you would confirm that the selective fuse meets the EUL compliance. And looking at the catalog again, you'll see that this particular fuse, there's a certification per UL file number E232989. Couple of other ones, factors to consider. Again, in this case, you want to take a look at the working voltage DC. And we said the working voltage DC for the circuit is 12 volts DC minimum. And in those fuses, the 6, 7, and 8 amp F1206HI are rated for 24 volts DC, which meets and exceeds the 12 volt DC spec requirement. The package size of 1206 just from the part number itself, you can tell that that 1206 package size would meet the requirement that the customer has presented to us. So in conclusion, the solid matrix F1206HI fuse series rated for 6 to 8 amps appears to satisfy all the application parameters specified. And to avoid possibility of nuisance blows, AM would recommend that the final section be made towards the upper side of that range. So either the F1206HI 7 amps or the F1206HI 8 amps would be the preferred choice. One thing to consider here, one thing that's really important is that, even though we've gone through this calculation and we've identified these two fuses as likely choices or preferred choices for this application, it's really important that the engineer that's considering these fuses actually take some of these fuses, request some samples and actually put them into the circuit and test the parts to make sure that they perform as expected. We've had several occasions where someone has come back and said, we have an unintended blow, something that's happened that we weren't expecting. The circuit seems to be operating as we might have thought, but for some reason or another, this fuse is opened. And in those cases, it may be something simple as a test probe applying an unintended spark or current to the fuse that wasn't intended, or it could be something in the circuit itself, which may require that we adjust the fuse rating slightly to accommodate more application-specific conditions. Here's basically I mentioned or I referenced the AM catalog, and here's basically circled in red or highlighted in red here where you would get the information that you were looking for in trying to calculate the fuse ratings from before. So you can see under the clear time characteristics, 1 through 8 amp, 1 second minimum to 60 seconds maximum. So you can see what the clear time requirements are. You can see the shape and dimensions. You can see the agency approval that they were looking for there. Confirmation of the voltage rating, the interrupting rating, and over to the right, I've circled the 6 to 8 amp parts. And you can see down to the lower left in that graph, we're 6.5 amps squared per second. For the lower of those three fuses, the I squared rating there exceeds the 6.21 amps squared per second of the circuit that we calculated earlier. And any supplier generally has this type of information available in their catalogs. So key takeaways in summary: fuse selection is not as simple as one might think. There are a lot of things that come into play in order to make sure that you choose the right fuse and that the fuse performs as intended and it protects the components within the circuit. Similarly, rated fuses can have different fusing characteristics, as I mentioned before: slow blow versus fast acting, one manufacturer versus the other manufacturer. And you always want to consider the lower and upper limits to protect components and avoid nuisance blows. Manufacturing differences can drastically affect performance in worst case conditions. You saw those pictures earlier on, and I've got some videos down here at the bottom that I'll show you here just quickly to demonstrate, what can happen if you select the wrong fuse and that fuse happens to be subjected to some worst case conditions. And the other thing, as I pointed out in the last slide, is you always want to confirm effectiveness of the fuse selection through real world testing and evaluation. So the fuse on the lower left down here is an AM fuse. It's being subjected to an overload condition, a worst case condition, and you can see I'm going to play this video and it goes really slowly, but you'll see when you look at it that that there's a slight flash, and sometimes it's difficult to catch that flash. Right there was a slight flash. Now that's the fuse opening. And the reason you're able to see that flash is, again, this is made of FR4 PCB material, which when it arcs, you're able to actually see that arc through the material. But please note that after that fuse is open, that there's no damage to that fuse whatsoever. This is another surface mount fuse of sorts. The next one to the right, it's actually an etched fuse that's on a board. And it's been pretty common in a number of applications if you consider how much less expensive it is to, when you're having a PCB board made, just have a fuse etched into the board as well. It takes up very little space, and it's low cost because you're actually manufacturing this fuse and placing it on the board at the same time you're making the board itself. But as you'll see from looking at this video, this fuse was subjected to exactly the same conditions as the fuse on the left. But once it sees that current, you can see what happens to this type of fuse. All right. The fact that it's not coated, the fact that it has nothing to contain that energy allows that fuse to open in a very catastrophic manner, and you can see the kind of damage that is done around the board. And then finally, here's one of the fuses that I showed in the pictures earlier on. This is an wire and air type of fuse that's subjected to a higher current. And this fuse here is probably a fuse that's been subjected to, I believe, 400 amps at 450 volts. And you can see what happens to this fuse from the video. So you can see the destructive manner in which that fuse opened as well. And in worst case conditions, this is not the worst case condition I've seen. I have other videos where the fuse has actually stayed in place. It hasn't tombstone like that. And when it stays in place like that, you get a redeposition of all of that material across that trace. You're supposed to have an opening there or a gap, but there's metal there that needs to burn off. And in those videos that you'll see, there's actually a lot of smoke and fire for an extended period of time until that metal burns off. And then the fuse will slowly open, all right, or that area will slowly open and prevent the current from flowing. All right, that's the end of my presentation. I'll open it up to any questions that you guys might have. Thank you very much.
Yeah, thank you, Mike. That was fantastic. If you could just say a few words about the different applications of slow blow fuses versus fast blow fuse, that would be fantastic.
Okay, so I covered them a couple of times earlier on. Fast acting fuse, basically you want it to open up almost immediately if it sees an overcurrent type of situation, because you've got an awful lot of components downstream, whether they're ICs or some other component downstream that are very sensitive to overcurrent, and they're very expensive, most of these components as well. So if you're talking about something like a home appliance where you've got a circuit board populated with a bunch of components, or you're talking about a computer, a laptop, a tablet, something along that lines, then you would likely want to use a fast acting fuse in those sort of situations. All right, because you want to protect things downstream. For a slow blow fuse, these are generally motor type of applications. When you think of a motor, think of something that would be like a drill, as I mentioned earlier on, a power tool, something like that, a cutting tool. Excuse me. So if you're talking about a jigsaw, for example, or some sort of saw that you're cutting through a piece of wood, and it hits a point where it's trying to cut, where it finds some resistance. When it finds that resistance, you don't want that fuse to blow. You still want the tool to operate. You actually still want it to cut through that, but it could snag on that. So you're going to get a high inrush of current to help you overcome that resistance. And that's where you'd want a slow blow fuse, because the slow blow fuse is able to accommodate those higher inrush currents without opening, and they'll still function after the fact. So that would really be the difference, some of the differences between where you would consider a fast acting versus a slow blow.
Excellent. Well, thank you so much, Mike. I really appreciate the information you shared and all the calculations. At this point now, we will end this recording. So let me go ahead and stop it.